In the heart of Chile's Atacama Desert lies one of the most advanced observatories in the world. These eyes on the sky have been at the forefront of ground-based optical astronomy for 25 years. The VLT, or Very Large Telescopes, have been instrumental in some of the greatest astronomical discoveries of all time. They have led to Nobel Prizes and transformed our understanding of the universe. In this special episode of The Sky at Night, I'm here in Chile at the VLT. These telescopes are operated by the European Southern Observatory, or ESO. It sits at 2,635 meters on the Paranal Mountain and consists of 4 8.2-meter main telescopes and an additional 4 1.8-meter movable ones. These telescopes can work individually or all together to see the finest of astronomical details, making this site home to the world's most advanced optical instrument with a long history of celestial firsts. I've come to meet the scientists and engineers behind this incredible technological feat to learn what it takes to run this flagship facility.
To see the sun setting here every night, it's still an amazing experience.
And uncover some secrets.
Welcome to The Sky at Night.
The Very Large Telescope is located at the Paranal Observatory in the Atacama Desert, one of the driest places on Earth, providing a perfect home for its state-of-the-art unit telescopes.
The VLT, or the Very Large Telescope, is actually made up of 4 main telescopes that can work as individuals or have their observing power combined. Each one of these beasts is 8.2 meters in diameter. The thickness is just 17.5 centimeters. Any thicker and they would collapse under their own weight.
Every day at sunset, the telescope dome opens up to the sky for the night. But over time, the mirrors accumulate dust, affecting their reflectivity and therefore image quality. Around every 18 months, the enormous mirrors have to be cleaned and recoated.
Cleaning a telescope mirror is a delicate and nerve-wracking process. The mirror itself weighs 23 tons and it's shipped from the telescope to this facility in its cell. Once here, the old coating will be removed and a new one applied. But we're incredibly lucky because the mirror is actually in this facility at the moment, and so we can see some of that coating process. Hello.
Hey, mate.
Maxime, lovely
Nice
to see you.
Yeah.
We're going to see the cleaning process.
Yeah, sure. Let's
Perfect.
go.
Head of Paranal's Maintenance, Support and Engineering, Maxime Bocas, is in charge of the operation.
Maxime, what are we looking at here?
So the dust is basically the dust that is in the environment, picked up from the ground by the winds and deposited slowly on the glass.
And so how often does this process happen?
We do that every 2 years because we find that it's in average the sweet spot for the astronomers that want a dirty mirror and for the engineers that have to do a heavy work to clean it. During these 10 days that we have to shut down the whole telescope, there is no astronomy, no science.
Yes, yes. So you do this as quickly but as delicately as possible.
Super delicate.
With the mirror safely removed from the telescope, it's time to start cleaning. Firstly, with a bit of good old soap and water.
They are going to start rotating this arm above the surface and pouring water first so that we can remove the biggest particle of dust. And then they will add soap. The soap will help to actually remove the stuck particles.
Yes.
And once we are finished with this first rough cleaning, we'll put chemicals on, and the chemical will actually remove the aluminium layer that is on the glass. And when we're happy that the thing is fully dry, then that's time to move it to the vacuum vessel.
After being stripped of its aluminium surface, it's time for the squeaky clean mirror to be recoated. This is where it will regain its reflective properties.
And so what will happen is once the mirror is cleaned, you'll take that, the bottom half and the mirror to that chamber.
Correct.
And that's where the sputtering takes place.
Exactly.
Yes. So can you explain what sputtering is?
What you do is basically you bombard a very pure plate of metal, the metal that you want to deposit, in our case aluminium, with ions.
Okay.
So it's like basically painting, because the mirror will be rotating under that plate. We'll be painting radial lines across the glass until we have done a full revolution.
So how much aluminium? Because I told, because we've got an 8-meter mirror, but how much aluminium is actually deposited?
It's very little. So I've actually brought a soda can here, all right? When it's empty,
Yes.
it's about 10 to 12 grams.
Yes.
And that's the amount of aluminium that will be deposited in a very, very thin layer on the mirror.
Cleaning and recoating a mirror of this size doesn't come without its challenges.
The challenge basically is homogeneity of the process. The whole mirror, because it's so big, the 40 square meter have to be cleaned the same way.
Yes.
And then, of course, doing the vacuum has its own challenges, depositing exactly the right thickness.
Yes.
So everything has to be adjusted like a watch.
When I was a child, I made my own little telescope mirror, just 150 millimeters across, and it went through the same process. But this is much bigger.
Much bigger.
Yes.
It's time for this freshly coated mirror to get back into action with some astronomy at the VLT. I'm travelling to the control room, a hub of astronomical discovery, to meet Joe Anderson, who is currently on the day shift.
Hi, Joe.
Hi.
So your title here, you're staff astronomer.
Yeah, I'm ESO staff astronomer.
Okay, yes.
So my job here is to work at night time, sometimes during the day when we're working at night. Then we're working with the telescopes, with the instruments, to take scientific observations for the astronomical community here at Paranal.
Joe is one of the astronomers who looks after the VLT's instruments, collecting data for other astronomers in different countries around the world.
So here we have four telescopes. On each telescope we have 3 different instruments. We're obtaining those photons on our instruments, and then that data is available pretty much in real time on the internet for people to download, and so the user then can download those data and start analysing those data.
Oh, perfect. That must be a lovely moment.
Yes, indeed.
Joe's time is split into thirds. 2 for ESO duties, like looking after the instruments, and 1/3 for his own research.
You also get the opportunity to do research of your own.
Yes, indeed. I spend some of my time doing my own research. I work in supernovae. So supernovae are the stars that explode, and my main focus is trying to understand which types of stars are going to explode with which type of supernovae.
And you've got some data to show us.
Yeah, so I can show you some spectra that we take here. This gives you information about the properties. So if you're looking at a star, it can tell you how much heavy metals it has. It can give you information, if you're looking at galaxies, of how many stars are forming in different parts of galaxies by using different, what you call spectral lines, that you see at different wavelengths, different colors within the spectra.
Joe and his team use an instrument known as MUSE, the Multi-Unit Spectroscopic Explorer, to help understand which type of star is going to explode.
So this is SN 2018 IE.
Okay, yes. A supernova that occurred in 2018.
Exactly,
Yes.
exactly. And then the image we show here in the middle, this is now just showing the places where the stars are forming. And so then we extract the information where the supernova occurred, but we also extract it in all these other places where the stars have been formed. And this is what's shown at the bottom. And the color scale here is basically the chemical composition. Oh. So then we can ask the question, well, is the chemical composition where the supernova exploded, is this higher or lower than the rest of these star-forming regions?
Have you drawn any
Yes.
conclusion?
We see it's much more probable when stars are forming at lower metal counts. It's more probable that these massive stars exploding in that place.
A supernova is more likely to occur where there's less metal density.
Yes, exactly.
Ah.
Which is strange, which has not really been predicted previously.
But it opens up a world of possibilities.
Yes,
and
indeed.
a better understanding of the mechanism of a supernova.
This is just one of the many scientific discoveries found using this incredible facility. It's time for a changeover as the night shift astronomers get ready to take over the control room, but not before taking in a spectacular sunset.
You've been working here for 10 years now. Do you ever get bored of it?
No, I mean, because it's such a unique place to work. I live in Santiago, in a big city of 6 million people, and then you come in here in the middle of the driest desert on the earth. So to see the sun setting here every night, it's still an amazing experience.
Yes, and I guess it's a precursor, because we see our local star, the sun, setting before it opens up the vista of the universe.
Indeed, exactly. So the engineers are getting the telescopes ready now, then they'll pass those telescopes over to the operations team at night, and then we're ready to start observing galaxies, stars, all the wonderful things in the universe.
Now that I've met some of the people here at the VLT, I want to find out more about what life is like when you live and work in a desert, and who keeps this mini town running.
This is the Residencia, an oasis in the desert where the astronomers, scientists and engineers, in fact everybody that keep the mighty telescopes running, live. It is quite impressive.
The architecture is so incredible that it was even used as a location in the James Bond film Quantum of Solace, and they left behind their fake rocks. There isn't much natural greenery here in the desert, but when you walk inside, what greets you is a very different story.
It feels quite tropical in here, especially compared to the marshinous desert outside. But like any good hotel, it's got all the mod cons, including a pool. It is amazing.
I want to know more about life behind the scenes at the Residencia, so I'm meeting someone who has been described as the Mayor of Paranal, Vanessa Pedro.
So, Vanessa, lovely to meet you. And you have a brilliant place here.
It is a fantastic place, yes.
Now, here at the Residencia, how many people do you cater for at any one time?
Per day, it's 150 in average.
Yes.
So we have, of course, astronomers, around 10, 20 astronomers, and all engineers, supporting staff, contractors. So as a head of the logistics and facilities department, basically, in 2 words, I try to make this place run smoothly and make things work.
Making sure everyone who lives and works here is well looked after is a priority for Vanessa and her team.
There is an expression, an army marches on its stomach.
Yes.
So how important is food here at the Residencia?
Food here, it takes a lot of energy, a lot of people. We, of course, take into account the different dietary restrictions of every single person of the 150 people that we have every day.
How challenging is it to get fresh food up to the mountain?
Well, it is challenging. We have trucks coming usually twice per week, and we have to keep everything fresh. It is a challenge, but that's why we have very high technology and very sophisticated equipments to keep everything up to the standards.
With many of the staff working night shifts, food is prepared around the clock, so no one ever goes hungry. As well as keeping everyone fed and watered, another key part of Vanessa's job is controlling the lights.
So we can see the canopy being deployed now.
Yes.
But why is this important?
Well, at night we have to avoid creating any interference, any light pollution for the telescopes. So yes, it's definitely not only closing this dome, the lights, but also closing any the shutters of the common areas or the rooms. Having all this light inside on the green, it's very important for the well-being. We have all these plants that create this warm atmosphere.
Because when you look out there, it does feel like an oasis in here. So with the canopy in place, it really does block out the light.
Exactly.
It is.
Well, it's a very efficient system. Yes, that's.
Vanessa's team also look after the leisure activities at Paranal to make a home away from home in the isolated desert. Ranging from ping pong to swimming, to music and to photography, they really offer it all. The VLT's full potential is unleashed when the telescopes work together, using a technique called interferometry. I'm meeting the physicist in charge, Dr. Françoise Delplanque-Stroebeler.
Lovely to meet you, and it's fantastic to be here on the platform of the VLT. So, how does interferometry play a role, and what is interferometry? It's quite hard to say.
We need interferometry because astronomers always want bigger telescopes for two reasons. One is to get more photons. It's why we have built those big 8-meter telescope, and we are building the future ELT, which is even bigger. But also the resolution.
So it's not actually about how much light you get, but about how big, physically big your telescope is.
Exactly. So what we do is to break this telescope in small pieces, in smaller telescopes that we combine as if they were part of the same big telescope.
I see.
So you take the photons that arrive to your telescopes, and they can interfere. They are friends. They can work together. The particularity of the VLTI is that we combine 8-meter telescope, and that nobody can do. And we have 4 of them. We can also combine them with a smaller telescope of 1.8 meter that can be separated by up to 200 meters.
Whoa.
So we reconstruct the image of a 200-meter telescope.
Although interferometry is an incredibly complicated process, the idea is actually quite simple. If all the telescopes are pointed at the same object at the same time, all the light can be combined to reveal even sharper details, like a much bigger telescope would. Below us are the tunnels that house the equipment that make this process happen.
You go first.
So here we come in the delay line tunnel, where the light is coming from the telescope, and the light is then sent to those mirrors that you see on the big concrete blocks.
Right.
The light is then sent to the other side of the tunnel, which is symmetrical from here on the other side.
So it's long. How far
It's-
down?
120 meters in total. And then the light arrives on those kind of carriage that you have there. So the carriage are moving on those rails that are extremely straight.
So this is the delay line, but how does the delay line work?
The delay line makes the photons wait for their friends.
I see. So it's like a waiting room for photons.
It's a waiting room, yes. Some arrive to the first telescope before the one coming to the second telescope.
Yes.
And to get the interference, they have to come back exactly at the same moment in the instrument.
The instrument, known as Gravity, has helped make some groundbreaking observations since it was installed. But every time light is reflected in the delay lines, photons are being lost, meaning astronomers are missing out on precious details. So the scientists and engineers at ESO are working on a way to bring those details into even sharper focus.
The Gravity instrument is going through a major upgrade to Gravity Plus. But the upgrade doesn't extend just to that instrument. The upgrade goes to the whole of the interferometric system and the adaptive optics system. The adaptive optics system is a critical part of the telescope because it takes into account atmospheric turbulence. It will also increase the sensitivity of instruments like Gravity.
Adaptive optics enables the images obtained to be almost as sharp as those taken in space. I'm meeting François' colleague, Dr. Frédéric Gunthe, who is working on this huge engineering project.
Gravity is a very specific instrument because this is an interferometric instrument, and they bring the light together in a single instrument.
But now you're going for Gravity Plus. What is that going to give us?
20 years ago, we used what was the best at that time. Now we have really developed the technology of adaptive optics, and now we are going to implement a system with 1,350 plus actuators.
Actuators are components under the mirror that adapt the surface to turbulence in the atmosphere and correct distortions. Laser guide stars will be added to each telescope, with 1 out of 4 already complete.
A laser guide star, the principle is really to project a laser on what we call the sodium layer. When you project this laser, you excite the sodium, and the sodium re-emits some light, and this light, we detect it as a artificial star.
Yeah.
And using that, we can go everywhere on the sky, because then we have always a star which is bright enough.
You make your own star, so
We
you
are
can
making our
monitor
own
it.
star, because we need a lot of light for this adaptive optic system. And if you're outside the galactic plane, whereas Milky Way, and you want to observe other galaxies, then here you have basically very few stars. Then it's difficult for you to have the right light. Laser guide star is there for that.
It's time now to put the improvements in place. Messy work that is only possible whilst the mirror is being cleaned.
But I suppose you're limited because it's the time that it takes to
Yeah.
fit the mirror. When the mirror is ready to come back, you need to be out.
Exactly. It's even worse, in fact,
Yes.
because we have a very short window. And just after this window, we have astronomers waiting for the telescope. Then if we are late, they
Yes.
lost their time. It would
Not
be horrible.
popular. Much of the work going on behind us is about the upgrade to Gravity Plus. But it's so much more than that. It's about an upgrade to the interferometric system, an upgrade to the adaptive optics system as well. And with all these different technologies coming together, it's going to lead to an amazingly cutting-edge system which is unique to the VLT. I can't wait to see what we're going to discover.
I want to learn more about the science being done here at the VLT. So this evening, I'm heading back to the control room. Dr. Abigail Frost is an ESO astronomer and has just started the night shift.
What's it like sort of living and working on a telescope like this?
It's a super cool and interesting job to do. It involves a lot of shift work. I mean, I'm based between here and Santiago, where I do my research. And so when I'm here, I'm mostly observing at night, dealing with all these consoles and all these lovely instruments. So at the moment, we are just doing some calibrations with the gravity instrument.
The power of gravity's data has already been used to solve a mystery. In 2020, a team of ESO astronomers reported the discovery of the closest black hole to Earth, located just 1,000 light years away, in the HR 6819 system.
They were looking at a group of spectral lines and trying to work out, okay, how are the stars moving in the system? If you have these stars in a stellar system together, you'd expect them to be moving around each other, but they weren't seeing movement from this star, they were only seeing movement from the other star. And that implied that it's moving quickly around something else.
Something else, yes.
Which we couldn't see. And so that's why they thought there was a black hole.
But another group had a different explanation. They believed the orbit could be explained by a binary star system, two stars orbiting one another. One of the stars was moving faster than the other, not because of something we couldn't see, but because it was stealing the other star's mass. Using the VLTI, Abigail and her team investigated which hypothesis was correct.
The VLTI was really like a missing piece of the puzzle in terms of us finding out the true origin of the story. We had two hypotheses, and we needed to check what was happening. And the way that we could do that is by looking at the distances between the bright stars. Because in this scenario, where we think that one has stolen material, they have to be very, very close together.
Right.
And that's very difficult to resolve. You need very high resolution, you need powerful telescopes or powerful methods. And for the other scenario, the stars would have to be far apart.
Is the mystery solved?
Yes, the mystery is solved. We got some data with the gravity instrument here at the VLTI, and this enabled us to identify directly where these two stars were. You don't need a black hole to explain this system. It's just
this
a
mechanism.
cool case of binary interaction and stars stealing material from each other and interacting.
Vampirism.
An explanation for the results Abigail and her team found is the occurrence of a vampire star.
Can you tell me, what is a vampire star and should I be worried?
So a vampire star is essentially a star that has stolen mass from another star, which is very close to it. We often have stars in these binary systems, and if they're close enough, they can steal material. Interferometry was really the key to cracking the case, and so that's why I love working with this technique. It's super powerful, super useful, and I want more and more people to use it.
The VLT is still a world-class observatory doing cutting-edge research. But here in the Atacama, there will soon be an even more powerful observatory. The Extremely Large Telescope, or ELT, is currently under construction.
When it's constructed in around 5 years' time, the ELT will be the largest optical telescope in the world. It's been built about an hour from the VLT, on a mountaintop. Now, I've spent much of my life working on large telescopes, so to see this monster actually being constructed is going to be mind-boggling.
When it is finished, the ELT will be about the size of a cathedral. Davide Diana is one of the on-site managers.
So I've been speaking about this place for over 18 years, and so to see it like this under construction is blowing my mind.
This is the biggest ever telescope ever built, with its 39.2 meter in diameter. We are talking about a major building that has a 60 meter in diameter, 3 meters deep foundation with roughly 9,000 cubic meter of concrete that have been casted.
Wow.
We are talking about the dome that will be moving, the rotating mass of the dome, for example, we are talking about 6,100 tons.
The ELT is being built on top of a mountain, 3,000 meters above sea level, providing prime conditions for observing. But before they get to that stage, they have a lot to get done.
So as we can hear, we're in a construction site with things happening all around us. So what is happening now? What stage of the telescope are we at?
Okay, so for the main structures, we completed the upper foundation, and for the dome, we are completely in the assembly of the first skeleton of the dome structure that is built to sustain the couple that it needs is the enclosure of the telescope during daytime, because the telescope must be at outside temperature when the door is going to be open.
Yes, and I've seen that before on other telescopes, like Gemini and the VLT. So you keep the internal temperature the same as the nighttime temperature. So when you open up, everything is peaceful, no
Exactly.
turbulence.
Another key challenge for this enormous telescope is earthquake protection. For each one of the 798 segments that make up the ELT's primary mirror.
So basically, they are laying on top of seismic devices to survive and to keep operating when earthquakes are happening. We have a complex system that also is a hydraulic control that allows the disengaging of these locking devices when a certain frequency and with a certain magnitude is acknowledged, is recorded.
And so with that hydraulic system, then the telescope is effectively floating on that system.
The engineering behind the observatory's construction is fascinating, but so is what it will be able to achieve, allowing in 20 times more light than a VLT telescope, so we can see other planets in more vivid detail.
My journey with telescopes began when I was about 13 years old, when I ground and polished my own telescope mirror. Now, at that time, the largest telescope in the world had a primary mirror of about 4 meters. But then along came the stuff of dreams, the ELT, the extremely large telescope. Here, the primary mirror of the telescope is 39 meters in diameter. I can't wait till it comes online.
It's time for me to leave the ELT and the VLT. This trip has been fantastic, meeting the scientists and engineers behind the amazing feats that keep these telescopes cutting edge.
I'm afraid that's all we've got time for from here at the ESO VLT. But do join us next month when we'll be having our Question Time special. In the meantime, good night.
Brian Cox and Robin Ince look back at some of the best moments from their hit science series. Listen to the Infinite Monkey's Guide 2 on BBC Sounds.